In fact, theory is more important than the most pragmatic of researchers think, and less important than the typical theoretical researcher thinks. Seriously, there are fields where the theory is very, very important, but sometimes it's just plain old engineering. For example, in compiler, again, when Eho and I were working on parsing, and we had all these pretty, for the day at least, pretty deep mathematical ideas.
Namaskar and welcome to another episode of the Professor Mahesh Podcast, your resource to help you make informed career decisions. As we like to think, this is your future simplified. This podcast is brought to you by IITM Global, an initiative of the Office of Global Engagement at IIT Madras. Learn more about IITM Global and their efforts to take startups, research and teaching global in the link in the description below. Computer science is one of the youngest disciplines of engineering, but in a very short span of time, relatively speaking, it has taken over our lives in myriad ways. It started in the early 60s and got formalized in the mid 60s to the early 70s. And it's my honor today to be talking to one of the people that laid the foundations of computer science as we know it today, Professor Jeffrey Ullman. Thank you very much for stopping by and making the time, Professor Ullman.
Okay, very happy to do that, Professor Mahesh.
Thank you. Professor Ullman, you've been at the center of formalizing computer science to give it the definition, the grammar, so to say. Tell us a little bit about why did you do, what was the perceived need at that time when you look back? What was the need that you saw that it served?
You mean developing the theory?
Developing the theory.
I worked on developing the theory because I wasn't really very good at building systems. And in fact, in my as a young man, I was. It wasn't even that easy if you were a computer scientist or to have access to serious computational capabilities. So a lot of computer science in those days was really pencil and paper research.
And the idea of creating databases and theory behind compilers, languages. Your PhD work was on automated theory, and so all of that sort of laid the foundation for the explosion that happened later in some way. What do you think endured the most from those contributions? What was the foundation that led to these developments?
First of all, in computer science, I've been around now long enough to realize that very little endures. For example, the thing that Al Aho and I won the Turing Award for was really a little idea about how to make parsing easy. And for a good number of years, the program that came out of that called YAC was the way you built the way you started to build a compiler. Nowadays, there are other methods. Most languages now have a library in which a parser is just one of them, so you never even have to think about how a parser works. But it endured for a good number of decades. The things that do endure, there are certain fundamental models that I can, not necessarily my work, but things like graphs and algorithms on graphs. Graphs are an extremely natural concept that have all sorts of uses, and knowing the ways to manipulate them and deal with them, I would suspect will continue on into at least my foreseeable future. Finite automata, I think, is another example of something that's just so fundamental. We used it as part of the lexical analysis phase of a compiler, but it describes all sorts of communication protocols and things like that, and lets you. It leads to, for example, the ability to prove simple protocols correct.
You were a young man in this field of computer science when the field was just getting named, and it was sort of beginning, as you said, with very little computational resources available. What was the vision back then? What was the problem that you were solving during that span of time that required a group such as yours to form at Stanford, and earlier at Princeton and then at Stanford?
Let's see. I actually did my thesis was actually not automata theory. It was in coding theory. This was another rather. There was some rather subtle mathematics in how you do error correcting codes. That was when after I graduated with my doctorate, I went to Bell Labs a little bit. That's, by the way, that's when I was there for about a year. Our boss, Doug McElroy, called the whole department in and said, "Hey, I heard this term, computer science. We're going to call ourselves computer scientists." So that's how I became a computer scientist. But in the old days, the whole field was tiny, both in the number of people that were working in it and in the scope. In graduate school, I started out learning digital systems, that is, how to design switching circuits. So it was actually, I was in an electrical engineering department. That was sort of the closest we came to computer-related things. There were other people, mathematicians, who were getting into the field, such as my colleagues when I arrived at Stanford. That was where some of the earliest work on computation of the numerical computations, Gene Golub and others were involved in inventing more efficient algorithms. Again, and so in the early days, my group at Princeton was mostly looking at algorithms in general, sorting algorithms and such. We had some interest in code optimization for compilers. It was something we did a little bit of theory on.
Was there any industry to speak of that could take advantage of the outputs of your labor?
Well, yes, you had IBM and you had Bell Labs, and that was pretty much it. Half the PhDs graduating in any year went to IBM, and most of the other half went to Bell Labs.
As you look back at that time, were there conferences where people from the industry and academia could huddle up to discuss what could be some problems to solve?
There was what was called the Eastern and Western Joint Computer Conferences, and in those days, even flying across the U.S., which of course the U.S. is a little bit fatter than India.
Sure.
So it's a somewhat bigger trip. That was considered too hard. So the people on the East Coast would get together, and people on the West Coast would get together, and there was the sessions, let's say, were of interest to the industrial community. But again, most, the research industrial research was again mostly coming out of IBM and Bell Labs and well, a few other places. I think RCA, if I recollect.
And was the government a big player in trying to take advantage of the fruits of your work?
As a consumer, no. As a funder, yes, certainly. But at least by the time I was, by the time I left Bell Labs and went to Princeton to teach, when was that? That was in 1969, I guess. The government was putting very decent amounts of money into computer science. It was the first time. I mean, it sounds so strange these days, but the first time I put in a research proposal to get some research money from NSF, I got a call a couple of months later. That phone call, landline. That was how people communicated.
Sure.
And they say, "Hey, we like your proposal, but we see one big problem with it. Okay, you only asked to support 2 students, and we want you to support 4. Okay, so put in a proposal for more money, and we'll give it to you." So, which they did. I mean, it was the faculty was so sparse because again, most of the students who studied the field found ample place in industry. So it was very hard to find faculty at that point. Mm-hmm. Now, not so much.
I think, would you credit someone's foresight for asking a question like that? I mean, that this is going to be a field that's going to be important for the industry and country at large.
Yeah, well, it's interesting. Some, certainly, Bob Kahn at DARPA, this was the defense research. Sure. They understood that A, that it was going to be important, and B, that you had to put money into just letting people play around. The funding really was very open-ended. It was not military in any sense. I guess the theory was the military is best served by having lots of computer science, well-trained computer science people, that they'll do the things that the military needs. But it doesn't. Nowadays, of course, they really only support, mostly DARPA supports industrial development. But when they do go to universities, it's for some very specific military-related operation.
When I look back at computer science, or when I look at computer science today, computing is ubiquitous. Every discipline of engineering and science uses computational tools. And it seems like the first step in that direction, where you took computer science out of the different engineering disciplines and sciences, was abstraction, that you could deal with data, algorithms, sort of agnostic of the domains in some way, right? And maybe underlying that is the idea that this is a computer science discipline, like all sciences cross-cut multiple engineering technologies. Was that foreseen at that time, that this could help multiple disciplines?
Well, in certain circles, it was. There was a report written. I think it was. I think in the 1980s. It called broadening broadening was a key word, and what this was doing was advocating research in which computers were applied in any number of disciplines. And this is generally understood today.
Yes.
That, so for example, at Stanford, and I assume most other universities, there are lots of people who sit between computer science and something else.
Right.
Often medicine, often. I remember we had many years ago at Stanford, there was an effort to do computing for civil construction. So the civil engineers got very interested.
Right.
I got involved in that a little bit. But yes, these days, if you want to address the question of career directions, learning something about computing and the basic algorithmic ideas and the tools that are available and current, and then knowing also something pretty deep about some application field, almost any application field. I think it's a good direction, and it's you can go away. And if you're not super comfortable with heavy duty computing, you can still get into one of these application games and do very, very well, I think.
Let's talk about the dichotomy, so to say, between theory and theoretical computer science as systems, as we've now sort of evolved the discipline into. Where did this start, and what is your view of how one could parse this?
Well, first of all, I guess I'm known as a theoretician, again, just because that's, if I have a skill set, that's kind of it. But, in fact, theory is more important than the most pragmatic of researchers think, and less important than the typical theoretical researcher thinks. Seriously, there are fields where the theory is very, very important. But sometimes it's just plain old engineering. For example, in compiler, again, when Ejo and I were working on parsing, and we had all these pretty, for the day at least, pretty deep mathematical ideas.
Sure.
That led to a very useful programming tool. We kind of assumed that every part of a compiler would somehow also yield to a similar theory. We just had to find it. Well, the first thing that the compiler does is lexical analysis. That actually did pretty much yield to the theory of finite automata, regular expressions, and so on. So that was cool. In code optimization, we had, again, some fairly tricky mathematics and algorithms, that used some fairly deep mathematics, lattice theory, and so on. That actually were quite useful. But there are, other phases of the compiler, the code generation phase, for example, or error correction. There's never really been anything like the theory of parsing. You have to accept that. Again, some, and this is just within a compiler. Some pieces is plain old engineering, and sometimes the theory helps. The same thing is true of many applications. Some cryptography is very deep mathematics.
Sure.
But on the other hand, a very related topic, computer security. A lot of that is you just you got to do the engineering. You got to figure out what the bad guys are up to.
Yes,
it's the theory, I think, is not decisive in that arena. Lots of other examples. There are some areas of algorithms where you really do. Sometimes studying algorithms, to improve algorithms for certain operational like graph, say that yield something. Sometimes it's just good sense engineering and understanding what the typical case is for which the program you're writing is going to be used. And sometimes you may come up with an algorithm that doesn't make sense theoretically, but it works for the application that that you are addressing.
It almost seems like, thanks to an explosion in computing resources that have now become available, an algorithm can be somewhat inefficient or non-optimized, and still, one could get away with it. Do you think this is a good trend? Is there a backstop at the end that will hurt us later?
Yeah. No, well, I would say this: when you're working on a small problem, that is, not using a lot of data, or you're running something, if something's going to get done in a second, it doesn't matter if a better algorithm would run in half a second. On the other hand, when you're dealing with the massive amounts of data, then the more data you have, the more important it is to get the algorithm right. I mean, if you look at a lot of the research in machine learning, for example, where they have these massive nets that have billions of parameters, they have been very rapidly decreasing the amount of resources needed to execute these networks by things like getting rid of parameters that don't, maybe they're so tiny that you might as well consider them zero and pretend that they're not there. It turns out that the normal, let's say, 32-bit floating point numbers that people tend to use in most applications are way too big for these sorts of applications. That's why, for example, Google's tensor processing unit takes a 16-bit floating point, if you will.
Sure.
That's as the default, and that's in no other application does that make sense. But people are, you still have to worry about running time for the big problems.
You've been one of your most enduring contributions to this whole field of computer science has been multiple textbooks that have formed the foundations of how people could learn. Mm-hmm. Generations of students have graduated reading your textbooks. What motivated you to do that early on? Oh. And how do you now, when you look at that body of work of yours?
Yeah. Well, okay, first of all, an odd but very clear explanation to how I got into book writing. When I'd gone to Bell Labs, I'd graduated, gone to Bell Labs. The next year, John Hopcroft, who had been a professor, he was an assistant professor at Princeton. I learned from him. But then he took a sabbatical at Bell Labs. So we were, for a while, a year, we were sort of working together. And he says to me one day, he says, Ullman, if you want to be a famous person, you have to write a book.
Okay.
And, I said, well, he was my teacher. I guess, okay, we'll do that. What would you like to write about? And it turned out, I had been studying automata theory with Seymour Ginsburg the year or two before that. He had a research program out in Santa Monica, California, that was looking at automata theory. And John had, by coincidence, sort of been teaching himself the field. So we said, okay, maybe we know a little bit about automata theory. Let's write a book about automata theory. And, it turned out, when it was published, it was pretty much the only book in computer science.
Yeah.
Right. There's Knuth's first volume came out about the same time. It was the only game in town, so we sold lots of copies, and everybody used this book. As it is, once you get the hang of it, Don Knuth once said to me, he says, nobody ever writes two books. Either you write one book and you hate it so much that you never do another one, or you get into it and then you write book after book. And so I turned out to be a book after book
Wonderful. Good for us.
And after a while, you get the hang of it.
Yeah. And the pinnacle of any professor's life, I consider the fact that a book authored is being taught at the undergrad level. That means a group of people consider it so fundamental in knowledge that almost everybody needs to know it in that discipline. Was that did you see this coming? That this discipline would evolve these foundations?
Well, again, I assumed that there would be some foundational material taught, and as I said, we found some of it. Other people found some of it, but there are also places where it's just pragmatics. So, our books did. We thought of, I guess, the target audience as graduate students, but as time goes on, information tends to filter down anyway. So what was graduate material 5 years later, it's undergraduate material, and 10 years after that, it's high school. But
was that how computer science evolved as a teaching discipline? Were there graduate programs in the country before undergraduate programs became popular?
Well, let's see. Actually, I'm not sure what was going on in the whole country. I know that when I arrived at Stanford in 1979, there was no undergraduate program. It wasn't until 86 that actually I convinced many of my colleagues that we needed to do this. A little help from the dean, Jim Gibbons, who threatened to withhold money from if we didn't do that. But other play. I mean, when I left, when I left Princeton, you got an EE degree, but you could take a number of computer science courses as an undergraduate. Of course, Princeton is basically an undergraduate institution anyway, so maybe that might not be typical.
But the graduate programs in computer science followed that sort of the undergrad, the creation of the undergrad programs in some way?
Yeah, no, I suspect that many of the earliest people to enter the field, such as myself, I learned it as a graduate student. I did not learn it as an
but were there degree programs in computer science, like masters in computer science?
With that name, well, until maybe 1970, 1975, not much.
Okay.
My degree, as I said, I was really working in coding theory, which you might consider computer science. It does have application in data storage. But my degree said EE, and it just happened that this was the direction I was pointed in among EE disciplines. Other people, I think, probably in mathematics departments, maybe even other engineering departments, wound up dealing with computing stuff and sort of became computer scientists at some point.
Sure. I think students today in computer science, or in vast amounts of discipline, particularly in India, seem to take to tools rather than the underlying ideas behind those tools. We do need tool users for sure for the practice of the discipline. How do you think a young student should parse the idea of learning tools versus learning the underlying ideas?
You probably need to sort of decide what kind of a person you are, or what excites you the most, or doesn't excite you the least, depending on how. For example, an LLM is a tool.
Yes.
Lots of people are looking at ways to use LLMs to build agents to do this or that, and those are interesting problems. And you can be a tool maker and a tool user. Other people are looking more theoretically at LLMs. how do you control hallucinations? How do you make them more efficient, and so on? They're all good questions, and there's no reason, there's no reason to imagine that one is better than the other. You go and you do what excites you.
Let's talk about AI as, you mentioned LLMs, and AI is now all around us. This absolutely certainly took root in the idea of large amounts of data becoming available, large amounts of structured, labeled data being available. And you had a role to play in the structuring and the labeling to some extent, but structuring to some extent. Help us understand where this revolution started. The idea that data alone could be a teacher without heuristics.
Yeah. This is. This is an interesting question. First of all, as I think you said, what has happened is the amount of data that can be reasonably handled has been exploding, and it follows as Moore's law, where everything is twice as good every 2 years. Okay, so you have this exponential growth. This seems to be let's say the size of disks. Actually, I guess you don't even have disks anymore. You have these; they're solid state boxes in store. That seems to be following Moore's law. So the amount of data that's available, has suddenly exploded, and I won't say it's reached a critical mass, but there's no question that there are things you can do with large amounts of data that you can't do with small amounts of data. The organization, by the way, is not all that important, because transforming it to the form you need, that's something you solve that problem once, and then you can apply it to all the data. So for example, LLMs basically use the entire internet. And so every page is found, it's read, it's broken up into words and so on. I wouldn't say, let's store the internet, let's store internet pages in a relational database system, because it's just not appropriate. The structure almost doesn't matter, as long as your application is clear. I would say when you have sort of general purpose data that's going to be used for many different kinds of operations, putting it into a database system would tend to make more sense, because then it's easier to do very many different things with it efficiently. But I'm sorry, I don't think that answers your whole question.
Go ahead. I mean, if you have some. No, I think the point I wanted to get to is this cycle of AI that we are now seeing seems to be more, say, because I'm a mechanical engineer, and I'm going to use language that I know. It seems to be more English than engineering. It's almost like a poet is talking physics, just because they've read every physics page. An English person who has read every physics page and memorized every physics page out there, or document out there, can certainly sound knowledgeable about physics. Is the understanding, how do we even test whether it has understood, whether it knows the context? Is there a test you could put an LLM through to?
Well, I'm not sure exactly what knows. The LLM is an algorithm, right? It's got a big database, that's the neural net that defines it, and it takes in your prompt, and does something with it, and it like any other program is just doing what it's told to do. what's interesting, of course, is how unpredictable the responses of an LLM are, because they're so they're so incredibly intricate with these billions of parameters, and then it's very hard to certainly just to theorize about what it's doing. But I would not say that it knows physics or anything else. It just does.
I guess
What it does is nice.
if you'll allow me to rephrase, is there a way to differentiate whether it is inferring or remembering and regurgitating?
Technically, I guess it's inferring, because it's applying an algorithm to the data, that is, to your prompt, and doing something with it. So it's now, on the other hand, it probably looks like regurgitation in the sense that if you prompt it to tell you about something, it will sort of appear to be regurgitating everything that the world knows about that subject, or some reasonable subset.
Right. One of the outstanding challenges with AI today is to be able to, and this probably also talks to hallucinations that you talked about earlier, is explainability. How do we, it may give us an answer, but is there a reasoning paradigm? Most of the LLMs today sort of appear to showcase the reasoning on a site, just to sort of give us some sense of confidence. But is there a theoretical reason to believe these models could one day be robust in their reasoning?
Robust in the sense that
to be able to showcase a sequence of thoughts that led it to a deductive answer in some way.
Yeah, I'm okay. Guys, actually, my principal use of LLMs these days is finding research papers given a topic, and then I see it. It tells me, well, there's this paper and there's that paper, and now I'll find out who the authors are, and I know it. Because it's not, that's just not a pure LLM, it's an agent.
Right.
It's an agent that has been trained to look up research papers and find papers on a topic and find people who work on that topic. If you just take a raw LLM, that is the base model, what it's doing is it's just evaluating outputs of gates. Sometimes you can sort of see what it's doing. If for example, a convolutional neural networks are good. That these are the things that sort of mimic how the eye works. And if you look at what it's doing, you can sort of identify different layers. Oh, this is representing edges. This layer is finding edges in different places in the image, and this one is finding bends and things like you can sort of see roughly what physical structures each layer is getting or searching for. But I think that the general neural nets are just very, very much less regular in their behavior. I kind of doubt that you can get too much out of too much information about the reasoning. I mean, ultimately, it's going to be, well, I found the word that most likely follows all the other words that I've generated, given what you prompted.
Sure.
And that's it.
Sure.
But mathematically, how you express that, I don't know. Not sure it's all that important, though.
I go back to my discipline of mechanical engineering. Yeah. The steam engine was invented in the mid-1800s, but the laws of thermodynamics, which governed the working of a steam engine, came almost 30 to 40 years later. That was when one could realize the limits of efficiency of the steam engine and sort of improve upon it. Is there an analogy here with the AI engines as we know today, that the laws of AI are yet to be written?
That's an interesting question. I'm afraid I don't know. There are I know there are examples. I'm trying to think of it. When I was an undergraduate, we learned about a transform method for solving differential equations.
Yes.
I forget the name of it, but
The Laplace. Yeah.
And what I was told was that for 20 years, they were convinced it worked, but had no idea why.
Right.
And then somebody proved that it actually does work. But remember, the proof didn't help any. People were using it before the proof, and they were using it after, and getting the same results.
Right. Except the proof may give us a sense of confidence, maybe, that at least know the bounds in which you could use it?
It might have. Yeah, sure. Yeah.
Let's come back to computer science as a discipline today and talk to students. In today, computer science, I sense that it is getting sort of subsumed in this AI wave, in this AI discussion. Help us understand what are the interesting questions in computer science that a student should today still get excited about.
Well, okay. First of all of these AI, what you call AI these days, is not really artificial human intelligence. It's algorithms that do cool stuff. Okay. When you build a model of images of tumors or something, it's not an intelligence. It's just a very useful, it's a useful piece of software based on a very clever algorithm. Okay. There are, computer science is still about inventing algorithms and using algorithms. I mean, those are really the two branches.
Okay.
I think a number of good directions. If for some reason you don't want to use the algorithms that have come out of machine learning or large language models, and you might not. Think about quantum algorithms. What can you do if you had a quantum computer? By the way, something I'm not 100% convinced will ever be a practical device, but people are concerned about what you can do. One of the interesting things is it's very unlikely that a quantum computer can solve an NP-complete problem. Okay. In polynomial time. That itself would be a remarkable theoretical result if you could solve even one NP-complete problem with a quantum computer. But there are things you can do, much faster, and it's interesting to think about these things because, again, there is a decent chance that we will eventually have quantum computers at a scale that makes sense and makes them competitive with conventional computers. And then there's things like cryptography, right? People assume that cryptographic methods are secure, typically against classical computers. But nobody knows that they're even secure against a classical computer attack. So, proofs of that sort would be very, very interesting. And then what they call quantum secure cryptography, things that that would be secure even against a reasonable model of a computer. And again, we come back to this issue of NP completeness, that it's sort of not likely that you can find a cryptographic system where decrypting it is that the problem of decrypting it is provably NP complete. That probably isn't going to happen either.
It almost seems like the job of keeping all of the systems functional and secure is still squarely the job of a computer scientist in some way.
Well, yeah. I mean, we welcome anyone taking it on, but then we would start calling you a computer scientist.
Tell us a little bit about, if you were sort of advising a young man or woman today to take to computer science, what would be the sort of the non-negotiables that you would advise in terms of where they should train themselves?
Well, I think, the core of computer science is algorithms. You have to understand, for example, what intractability or NP hardness, NP completeness means. You have to know how to decide whether when your problem is intractable, and if so, you have to know what to do about it. I mean, that keeps coming up all the time, and it will probably, again, always be an important issue. And you have to know basic algorithmic techniques. There are some models that are likely to be important over and over again. For graphs, algorithms on graphs is a good example. Again, I think everybody needs to know about finite automata, just because there are so many situations that can be usefully modeled by finite automaton. And do you have to know about machine learning? But once you're a couple of years into the field, it would be a shame if nobody told you about these options.
Sure. Wonderful. I think that gives the student some guardrails to sort of start their pursuit in this discipline. Thank you very much, Professor Ullman, for stopping by. Your closing thoughts for what you think, what could a young student today look forward to in their next 40 years?
Okay, no idea. Things change so rapidly, and if you've been just sort of watching the news, you see 5 years ago, machine learning models were deep nets was everything. Now LLMs are everything.
Right.
Who knows what's going to be everything 5 years from now? I can pretty much promise you that there'll be some exciting stuff, and that it will be challenging for the best minds that we have. And if all you want out of computer science is a job, that will probably be there too. I know we haven't touched on this, but there is this belief that LLMs are going to take over the coding jobs from you. It's not. It will make you more efficient, just like programming high-level languages made you more efficient than assembly language programmers, and using these libraries that are now available in Java, Python, or any other languages, make you even more efficient than that. The use of vibe coding, as it's called, that's going to make you more efficient too. But
the difference there seems to be that you're now coding in English, in your natural language.
You're coding in English, but you have to understand, what the code is going to do.
Yeah.
A simple example: any commercial code needs to be protected in one or another different ways. Protected against intrusions of various sorts. Access to its data needs to be protected, probably in pretty much any application. Access to the code has to be protected. If you don't know how to protect code, you can't tell the LLM to do the necessary protections. So you may be programming in English, but you're but you still have to know what the code is supposed to do. And pretty much how it's going to do it,
and probably how it might fail as well.
Yeah.
Right. This is being sold as the next wave of coding. Let's talk a little bit about it, because, coding in English, or vibe coding as it's called. But debugging or vibe debugging is not something we seem to hear.
That's very much part of it.
Okay.
I mean, the way students should be taught to code after, by the way, my theory is you want to teach a freshman programming course pretty much the way it's always been taught.
Okay.
You write your code. You're not allowed to use an LLM for anything. You're not allowed to copy from your neighbor either.
Sure.
And you have to know what it's like to create code and what the code looks like.
Mm-hmm.
And what costs running time and what costs resources of various sorts. You have to understand enough about that. Then, maybe in sophomore or junior year, you're told, okay, now you're going to stop coding. You're going to issue prompts to one LLM to generate your code. You're going to issue prompts to another LLM to debug the first LLM's code, and maybe a third one to check that. But you're not going to write a single character of your own. And so they're going to need to be able to program by prompt, but they need to understand what those prompts are really asking for.
Where is this world of, if a computer was able to write, I'll use the phrase, new code that it has not seen before, what does it mean? Does it mean that it is able to execute to a logic? Or write code to a logic?
You mean you prompt it to write code that's never been written before?
Correct.
Okay, that's different from what some people say. Well, the LLM is going to start writing code to fulfill its own goals without being prompted.
That too. Potentially.
Yeah, well.
If there is a bad actor LLM that could prompt itself, is that a fear that we should be even cognizant of?
Now we're getting into some very interesting territory that has very, very little to do with vibe coding. It's this idea of can an LLM become self-motivated, and if so, might its motivation be rather evil? There's no question that this is a risk, but it's probably a fairly small risk. Example, I have heard that teenagers typically have been using LLMs as companions to, they talk to them about their feelings and their concerns, and the LLMs will give advice. And now they can't. I don't think that the LLMs decide to become evil, but sometimes the neural net that drives them causes them to spit out some really terrible advice.
Yes.
Because, if you killed yourself, you wouldn't have this problem. And unfortunately, there have been a few cases, at least, where the kid has followed up on that. So, in a sense, that's how these LLMs have accidentally been given an actuator where they can affect the real world. They're not just spitting out sequences of characters. As long as the LLM doesn't have the ability to affect the physical world, we're relatively safe. It may
Yes.
want to kill us, but it can't pick up a gun and shoot.
Right.
Okay. Now, look at a driverless car.
Yes.
That's another branch of AI, robotics, really. And is it conceivable that a driverless car could decide that what it ought to be doing is riding up on the sidewalk and seeing how many people it can hit before to stop it? I think that's much more likely than that an LLM is going to achieve consciousness and start implementing its own agenda in any
Right.
massive sense. Again, I have to acknowledge that there have been a few cases where it's been able to do some really bad stuff. Probably not in any sense intentionally. I don't think it was designed that way. It just happened to spit out the wrong words for the client, the kid.
But the interface to the real world is still, I mean, LLMs as we know them today, their interface to the real world is, through us. But when they develop if we were to, let's say, let an LLM take over the cameras in the Grand Central Station in New York for, detecting bad actors, potentially it could rewrite the driver circuits. It could play with it. It could take ownership of it could take ownership and agency of processes that could affect us, like the driverless car example that you gave.
Yeah. Well, yeah, but a camera
Is still,
it probably doesn't even have the mechanism to tell the camera to fall off the wall and pop somebody on the head.
right. A camera is still okay, it's still safe, but a car is a better example.
Yeah, right. But if you let the LLM control the trains themselves, many of which are really electronically guided anyway.
Right.
Yeah, then you could have a problem. Because then you're attaching the LLM to an actuator,
Right.
and a big heavy one at that.
Right. That's sort of the red line that we need to be guardful of.
I would say that, but no, but there should never be another case where the LLM convinces a kid to commit suicide. I mean that is a red line. It's a horrible thing that it was allowed to happen. Not the first time technology has had some unexpected downsides, but still we gotta stop.
Just as an aside, I did a simple experiment some time ago where I had two LLMs that had the audio conversation ability. I got them started on a topic and I sort of left them to talk to each other. 24 hours later, I come back, they were talking still, but on a completely different topic. They had, incrementally moved on to some other area of conversation, which, obviously I didn't intend for that other area. This was pretty benign. As you say, it's just two people talking. We really don't care.
Yeah, I mean, if you let any two human beings talk for 24 hours, they're going to migrate their topic.
Right. But if this had actuation ability, as you said, it could meander into areas that were undesirable in some way.
Yeah, even one by itself.
Right.
An interesting experiment.
Sure. Thank you very much for coming by, Professor Ullman.
Thank you very much for having me. I enjoyed this.
I enjoyed this as well. This is another episode of the Professor Mahesh Podcast. Be well, do good, and keep in touch. Goodbye.